So I am honored to introduce the resource person of our first FDP session, Professor Debasis Dutta, a distinguished academic with over 37 years of
Hello,
teaching
sir.
experience, is currently a professor in the Mechanical Engineering Department at IIEST Shibpur. He holds a
Hello,
PhD in...
am I audible?
Yes, sir, you are absolutely audible and visible.
Okay, fine. Thank you.
Okay, sir. Professor Dutta, a distinguished academic with over 37 years of teaching experience, is currently a professor in the Mechanical Engineering Department at IIEST Shibpur. He holds a PhD in Mechanical Engineering from IIT Kanpur and a Master's and Bachelor's in Mechanical Engineering from Jadavpur University. Professor Dutta's expertise spans areas such as ultrasonic non-destructive evaluation, acoustic wave propagation, and ballistic impact of materials. He has guided 7 PhD theses and numerous MTech and PTech projects. A prolific researcher, Sir has published extensively in peer-reviewed journals and has been granted a patent for his innovative work in composite pipe manufacturing. He has also contributed to several international events as a speaker. In addition to his academic contributions, Professor Dutta has played a key role in curriculum development and course restructuring at IIEST, particularly in areas of machine design, finite element methods, and composite materials. So, sir is already here, present right at this platform. I would request, sir, please unmute yourself, sir, and please start your session.
Hello, is it visible?
Yes, sir. Your PPT is visible.
The first slide is visible, no?
Yes, sir. Just you, sir, you just go for the slide share.
Yeah. Is it visible now? It's fine?
Yes, sir. Absolutely fine.
Okay. Okay. Good evening to all of you. And first of all, I would like to express my sincere thanks to Honorable Director, Principal, heads of the departments, and faculty members of Elitte College of Engineering, ECE, and inviting me to as a research person for this 6 days online faculty development program under the auspices of ATAL Academy, and it is being organized by the Department of Mechanical Engineering, Elitte College of Engineering. So thanks to all the organizers, and also thanks to the participants who have registered for this program. And I am particularly thankful to the coordinators, Dr. Onimesh Talapatro and Dr. Rakesh Kumar, for their constant encouragement and keeping in touch with us, and helping us and keeping us updated regarding all changes wherever there were. So my topic is on finite element analysis of field problems in isotropic and orthotropic materials. So basically, I will be speaking on orthotropic materials, which are related to composite materials, because that is the theme. The theme is modeling and simulation of composite materials, fabrication, characterization, and applications. Okay. This is the second slide, and the presentation has two parts. Part one is numerical simulation of stress analysis of composite laminate made of orthotropic laminae actually under uniaxial load. This is a simple case of loading, but still there are certain insights that may be of interest to the research scholars or research students. The second part will involve with numerical simulation of ballistic impact phenomena of composite materials, which may be used as armors in defense industry. Now, composite materials are commonly used in structures. They may be used as for high mechanical performance. But the main thing is that these materials have got high strength to weight and stiffness to weight ratio. That is to say that their specific weight and specific stiffness are very high. Their absolute strength and stiffness may not be comparable to that of standard materials like steel, etc. But when it comes to specific weight, that means specific strength to density ratio or stiffness to density ratio, they have higher value. So naturally, wherever weight saving is a premium, stress analysis of composite structure becomes essential. And to predict their strength and prevent premature failure, finite element analysis is the most versatile and comprehensive numerical technique. And nowadays, it is very popular. And commercial software packages are also available using these finite element methods. Like ANSYS, Abacus, Adina, these are very popular and available. ANSYS and Autodyne have been used here in this work, whatever I am going to show you. Now, materials can be classified basically based on their stiffness matrices. First one is isotropic, which is the most common one. Isotropic means that they have identical properties in all directions. And secondly is orthotropic. Orthotropic is neither isotropic nor anisotropic. That means they have different properties in different directions, but there are some planes of symmetry. They are called orthotropic. And anisotropic are those which are their properties are different in all directions. They are also known as allotropic materials. And depending on their properties, they have got different numbers of stiffness constants. Isotropic has got two independent elastic constants, namely the Young's modulus and Poisson's ratio. They also have shear modulus, bulk modulus, but those are dependent on these two. Similarly, orthotropic materials have got four independent elastic constants in two-dimensional cases, and anisotropic materials have got 21 independent elastic constants. And our discussion will be on orthotropic materials. So this is the scenario, composite materials made of two or more constituent materials. What is a composite? Composite is nothing but where there are more than one constituent. And these constituents are macroscopically visible. They are visible on a macroscopic scale. That means an alloy is not a composite material. But if you break a concrete slab, you can see the reinforcement of steel rods. So steel rod is visible if you break the concrete. So we can say concrete is a composite material. And in the village side, you will see mud houses. The mud houses are made, but for better stability and strength, they are given this kind of, we call it in Bengali as beda. Okay, so they are put in between them. So they act as reinforcing elements. So that's a composite. So generally in engineering applications, composite materials are layered, and you can have fiber, you can have matrix. Fibers are the reinforcing agents, and matrix are the continuous phase. So when a lamina apply is made of fiber and epoxy. Epoxy means epoxy is one of the matrix materials. Fiber and matrix. Then we call them a lamina. So a lamina is very thin, and it is treated as a two-dimensional structure. So a lamina as a single body cannot be used for engineering applications. So what is done? They are stacked one over the other, and several lamina and ply, when they are bonded into a solid, then we call it a laminate. and the laminate property can be changed and can be designed, or I should say can be engineered, depending on different fiber orientations. So that depends on the choice of orientation of different laminae having fiber orientations in a different manner. So in this last part, composite laminate, here is a drawing. There are 3-ply laminate which can be used for some structural applications. This is a typical diagram that one of my students is making a composite laminate. Here you can see that this is the a ply, then it is being laid upon one over the other, and in between this epoxy resin mixture is being actually applied on the surface by a brush. This is a hand layup technique. It's a simple technique, and when we apply brush, then in the liquid some bubbles may be there. That bubble is to be taken out, and that's why a rolling action is very important, because if you have bubble inside, then that will act as a void when the laminate is cured. That is not desirable. So that will be remaining inside that laminate as a flaw. So no one wants a flaw. And after that, this is put in some device. There are molds. So we put them and let them cure for say 24 hours. It can be done with heating or without heating, but sufficient pressure is to be applied. And to keep the thickness uniform of the laminate in all directions or all portions, we need to put some spacer depending on the number of plies that have been laid upon. And finally, after curing, we get the final laminate. This is here the ply is a Kevlar 29 ply cut from Kevlar 29 mat, and the mixture is epoxy resin and hardener. So the rest of the things are there. Now this I have mentioned that fiber composite laminae are among the class of orthotropic materials. They are in between isotropic and anisotropic. Somewhat you can say that orthotropic material is a material with limited anisotropy. And the elastic behavior of an orthotropic lamina, as I said in the previous slide, characterized by 4 independent elastic constants. We will see who are they. The elastic constants may be expressed by rule of mixtures. So rule of mixture can be applied to find out some of the properties of a lamina. This is the thing that I was telling earlier, that here it's a ply in this fashion. In the next lamina, the fiber orientation is different. Here it is different, here it is different, here it is different. So this way, according to the plan, it can be stacked, and then finally they are all bonded in order to make a complete laminate. This is some of the relationships that we use in rules of mixture. That is, this is called a very important parameter, volume fraction of fibers. That's why VF. So this is the ratio of the total volume of fibers by the composite volume, assuming no void is there. And this is a weight fraction. Sometimes weight fractions are also necessary. That is total weight of the fibers divided by total weight of the composite. And it can be shown that sum of volume fraction of all the constituents we make to 1. Similarly, for the weight fractions also, sum of their individual constituents will make it to 1. We can also find out the density of the composite by this simple rule, rho I Vi, and I is the ith constituent, rho is the density of the ith constituent, Vi is the volume fraction of the corresponding ith constituent. So it can also be expressed as this. This is a relationship between weight fraction and volume fraction. And this. This is an important thing, that if a laminate is subjected to a load PC, composite force, then that is distributed. What's happening? Yeah, I think I was here. Is it visible? Hello?
Yes, sir, it
Okay,
is visible.
is it okay?
Yes, sir.
Okay, fine. So here this is a load on the composite, and that is divided by fiber load and matrix load. And this is the composite stress. This can be shown that it is sigma of sigma I Vi. That means individual constituent stress and its volume fraction. So we multiply and then add them up and get the composite stress. Similarly, we can also find out the composite Young's modulus, which is in the longitudinal direction, sigma Ei Vi, where I is the ith, Ei is the Young's modulus of the ith constituent, volume fraction Vi is the ith constituent, then product is summed up to get the total Young's modulus of the composite. What is important is that this relation Pf by Pc, that is sigma f Af by sigma f in this can be manipulated to this expression. Now, if we use a system where it is made of glass fiber epoxy we have discussed, and volume fraction is 10%, then also this for this glass epoxy, this Pf by Pc ratio is 0.69. That means 69% load is carried by fiber, where the volume fraction is very merely, fiber presence is very small, 10%. Whereas if it is 50%, then 95% of the load is carried by Pf of Pc. And if it is carbon epoxy, then its Ef by carbon Young's modulus is very high, carbon fiber. It is 100 times more than epoxy Young's modulus. In that case, even with 10%, 91.7% load is shared by fiber. And if it is 50% volume fraction, then 99% load is shared by fiber. So fiber is the main load carrying agent, and role of matrix is to bind the fiber, keep them intact. And failure mechanism and strength, if we have a look into this, when the load is applied in the longitudinal direction, then composite strain, fiber strain, matrix strain are all same. But since stiffness of fiber is very high, so failure stress of fiber will reach first, and then the composite ultimate strength is when the fiber is reached its failure strength. So sigma Fu Vf plus sigma m at epsilon f star. When the failure takes place, epsilon f star is the failure strain into 1 minus Vf. 1 minus Vf is nothing but Vm. So from this, we can derive a minimum volume fraction of fiber volume, minimum fiber volume fraction of fiber, and also critical fiber volume fraction of fiber. So there is a difference between the two. Difference is that if the volume fraction is below this fiber minimum, then effectively the load shared by the fiber is not effective. Whereas if the volume fraction is less than critical volume fraction, the fiber is not strengthening the composite. As if it were made of the matrix alone, then it would have it could have worked well. But if we want to increase, or if we want to put some strengthening effect by the fiber, then the fiber volume fraction must be greater than the critical fiber volume fraction. That is the concept of these expressions. So these are some of the rule of mixtures. One rule of mixtures I showed earlier, that EL equal to sigma EI VI. Now there are transverse properties also there. Transverse means perpendicular to the fibers. So that is we call transverse direction ET, and this ET will be this. Instead of a simple linear combination, it is a reciprocal combination 1 by sigma Vi by Ei, and GC or GLT, shear modulus, that is also an inverse summation formula Vi by Gi 1 over sigma Vi by G. But these things or these predictions of transverse properties by rule of mixtures does not seem to be good if we do experiments and look at the experimental results. So that is why Sai and Halpin, these two fellows, they are very famous in composite industry. They derived these semi-empirical relationship, and by which we can calculate ET and GLT by these empirical, semi-empirical, I should say. Some part is experimental, some part is theoretical. They did some curve fitting and then obtained this sort of equation. But these do well, and their results match well with the experimental observations. Similarly, these are some failure criteria. So I am skipping this slide. Now I come to this state of stress of a principal material directions in a lamina. Now here you can see one thing, although it is analysis of an orthotropic lamina, state of stress along principal material directions. Here it is principal material directions. Why it is called principal material directions? Because the stresses are being applied along the fiber direction or perpendicular direction. So when the loads are like this, then we call this as principal material direction. Now here it is the stress strain relationship is simple because the property EL, Young's modulus in longitudinal direction. Longitudinal means along fiber direction. These lines are fibers. So EL in this direction and EL in this direction, they are same. And ET in this direction and ET in the bottom direction is also same because they have the planes of symmetry. So if we look at their stress strain relation, this is the three-dimensional, but when we reduce to this, then it looks like this. Sigma L, sigma T, tau L T, Q11, Q12, 0, Q12, Q22, 0, 0, 0, Q66. We must look into the nature of the stiffness matrix. This is the stiffness matrix because this is the stress vector, this is the strain vector, and this is the stiffness matrix. Now in the stiffness matrix, these first two elements in the third column, they are 0. Similarly, first two elements of the third row are also 0. This has a significance. Significance is that if we apply sigma L, that means just a normal stress in longitudinal direction, there will be development of epsilon L. There will also be development of epsilon T. Normal strain in longitudinal direction, normal strain in transverse direction because of Poisson's effect. But there will be no gamma LT. That means there will be no shear strain because this is 0. Similarly, if I apply sigma T alone, there will be epsilon L due to Poisson's effect, due to this Q12, and due to this Q22, there will be a direct transverse strain, normal strain. But as usual, there will be no shear strain because of this 0. Now, if I apply only shear stress, tau LT, there will be no normal strain, only shear strain because of this Q66. So all these Qs can be evaluated in terms of Young's modulus of an orthotropic material. Q11 is this and this. Here 1 minus nu LT and nu TL. Nu LT is minor Poisson's ratio. Nu TL is minor Poisson's ratio. They have relations. So there are actually 1, 2, 3, 4 and 5 constants are visible. But nu LT and nu TL are not independent, they are dependent. So basically, in an orthotropic lamina, in principal material direction, they have got 4 constants. 4 independent constants, I should say. What are they? EL, ET, nu LT, and GL. these four. Nu TL is a function of nu LT, EL and ET. But this is a lamina where you can see the fibers are oriented at an angle theta with respect to any structural axis x and y. Whereas this L and T are the principal material directions. Here, as expected, these are transformation equations. This stiffness matrix, if you look at this one, sigma x, sigma y, tau xy equal to Q11 bar, Q12 bar, Q16 bar, Q12 bar, Q22 bar, Q26 bar, Q16 bar, Q26 bar, Q26 bar. These epsilon x, epsilon y, gamma xy are the strain components in any arbitrary xy direction. And compared to that, as I said earlier, when it is LT and T directions, then the matrix is not fully populated. These elements are zeros. But here it is fully populated. It means what? It means even if you apply only sigma x, there will be epsilon x, epsilon y, gamma xy, all strain components will be developed. And how they are related? They are related by these transformations. So Q bar matrix is there that can be generated by Q matrix. Okay, so this is the scenario. If it is an arbitrarily any fiber orientation theta, then the deformation of the lamina will be arbitrary. Arbitrary in the sense, if it were a rectangle, after application of load, it will become an arbitrary quadrilateral, because there is everything. There is elongation, there is contraction, there is shear deformation. So a rectangle does not remain a rectangle, it becomes a quadrilateral. Whereas in case of principal material direction, rectangle becomes a deformed rectangle. The shape does not change because there is no shear strength. Next we go to laminate. As I said that a single lamina cannot be used in practice. So several laminae are stacked together and we get a laminate that can be used for structural application. And it is the laminate they can be which are subjected to general loading. You can see this NX, NX is here, X direction. That is a pull. There is a pull in Y direction. There is a shear load NXY, and there are twisting, bending, everything is there. So all these things can be taken care of by doing the Kirchhoff's hypothesis. It is actually the classical lamination theory, CLT, based on Kirchhoff's hypothesis. Those who have studied, they know very well. And here the concept is the strain components at any layer measured with respect to geometric mid surface, that is a mid plane strain plus Z times kappa. Kappa is the plate curvature. And this can be related to the sigma x, sigma y, tau xy is related to epsilon by virtue of Q bar. We have discussed about Q bar. And the loads and the moments, they are related by this equation. So this is what about classical lamination theory. The load moments can be expressed in terms of stiffness and the strain components. And finally, the load is expressed as this stiffness matrix A times mid-plane strain plus B curvature. So what is the beauty of this equation is that it tells you clearly that even if you apply the forces, in-plane forces on a laminate, there will be mid-plane strain, that is fine, but also there will be curvature. There will be curvature. And similarly, if you apply only bending moments or twisting moments, then there will be curvature, fine, because bending, twisting will create curvature due to this matrix. But also there will be extensional strain and shear strain in the mid-plane due to this matrix. This B is here also and here also. This is actually called coupling stiffness matrix. This coupling is there because the existence of B matrix. Why do you call coupling? Coupling means curvature is an out of plane displacement. This is related to in plane loads. Generally, in an isotropic material, if we apply forces, there will be normal strain, shear strain, but no curvature. But if it is an orthotropic laminate made of orthotropic lamina, generally orthotropic laminate, then of course you will have this coupling effect. But there is a way by which this coupling can be reduced to zero. That is by using symmetric matrix, symmetric laminate. So extensional stiffness matrix will always be there. Bending stiffness matrix will always be there, but coupling may be made zero if we make a symmetric laminate. And when these loads are known, then we can find out this epsilon 0 kappa, and from there we can calculate strain at any layer, and from there stress at any layer, and then we can calculate sigma LT at that layer by doing the stress transformation. This is the, in brief, the classical lamination theory. But what we are going to discuss here briefly, that if we take the case of a laminate of this type, you can see that laminate. This is a laminate. This problem was first considered by Pipes and Pagano long time back in 1970. So what did they do? They took a laminate which is symmetric also. Therefore, there should not be any coupling effect, and they are pulled by an uniaxial. Now, obviously, as per the classical lamination theory, B matrix will be zero. So therefore, there should not be any stresses at the three-dimensional state of stress. Only in-plane stresses developed inside the laminate. This is a 4-layer laminate plus minus 45 S. S is symmetric. Theoretically, as per classical lamination theory, there is no coupling between in-plane load and out-of-plane curvature. But experiments tell a different thing. Experiments tell that when failure takes place, if you keep on increasing the load, then when failure takes place, it takes place at the edges. At the edges, what happens? There is delamination. You remember that a laminate was constructed as different plies or laminas, but these laminas get separated at the edges only. This does not happen at the middle. It only happens at the edges. So something at the edges, there is something. That is why failure is taking place. Once failure is initiated at the edge, this propagates through the interface or interlaminar or the space between two lamina, and eventually leads to the laminate failure. So this is called edge delamination. So this was revealed experimentally, and Pipes and Pagano, they were trying to give a reason why this is happening. So that means classical lamination theory is good for the middle part, but not for the entire laminate. This is a lesson, because classical lamination theory is treated, we also teach, and students get an idea or impression that, okay, classical lamination theory can tell everything. No, it is not. And that is what I am trying to show you. Pipes and Pagano actually solved the governing equations by finite difference method, and they showed the result like this. If you look at this, you can see that this tau x jet, this is the width, y by b ratio. When b is maximum, then it is 1. So it's a normalized y by b. And you can see after 50% of the width, 50%, this tau x jet starts increasing. And at the edge, extreme edge, this is a very high value. Okay. may not be the normal stress, but this shear stress has high value. And this transverse shear actually causes the initiation of delamination. It first happens at the peak, and then if you keep on the laminate stressed by your uniaxial load, then gradually the delamination is expected to increase, or if there is gradually the load is increased. So this edge delamination will propagate to cause the eventually failure of the laminate. That is not desirable. So we must be very, very careful to study what is the distribution of tau exchange, which the classical lamination theory is not able to do. So this results of Pipes and Pagano, this I have shown you. And next, we tried to do this on ANSYS. So what we did is actually we created the model in the ANSYS environment and tried to simulate it by using, as you know, that finite element has got some steps. The first step is discretization. That means dividing the entire domain into small segments of similar things, similar components that are called elements. And these elements are connected to each other by nodes. Now, there are several types of elements available in the ANSYS library. Some are shell type. If the element is very thin, then you can make use of them, and they mostly try to capture the two-dimensional effect. Then also there is solid shell element type. They are somewhat in between shell and solid and layered solid elements. So there are three types elements are there. So these are the dimensions. First of all, the same laminate configuration is used. Then these E11, E22 properties are there. Since it is a plus minus 45 degree and transversely isotropic. So E22 and E33 means actually ETT prime. So they are this value. Then nu1, nu2, these are the Poisson's ratio. These are the shear modulus. And for the loading, this uniform axial displacement 0.3 millimeter is applied at the faces. This is our X face. So at this end, displacement is, it's a displacement control loading. Now, first shell 181 element type was used. And what we got? We got this. We got sigma x, sigma y, tau xy. But we did not get any appreciable value of tau xz, tau yz, etc. So that means shell 181 element is not able to capture this three-dimensional state of stress phenomena at the edge. That's the limitation of this element. Then slosh 190, another 8-noded solid shell element. Solid shell elements are better than shell, but they have got limited three-dimensional state of stress capability. So this was also tried, solid shell 190 element. Solch. Together they call Solch in ANSYS. But the later versions of ANSYS, I don't know whether they have the same name or not. This was also tried, but Solch 180 also could not provide this edge phenomena where the tau xz and tau yz are actually expected to be a high value, which initiate the edge delamination, what is observed in the experiments. So the search still goes on. Lastly, solid elements are tried. Here, solid 95 element is used to discretize the laminate, other things remaining entirely constant. It's a 3D 20-noded homogeneous structural solid element. but with layered capacity. And 3 degrees of freedom per node is there, x, y, z direction. This is element shape. I don't know where from these lines are coming, right, tick, and etc. Okay, so these are the property. This is the laminate, and this is discretized by solid 95. This is in ANSYS forum. Here you can see. So appropriate boundary conditions are. Now here you can see that the tau xz in this purple line perhaps, that is being shown when we use the solid 95. So here, this high shear stress at the edge, that can be captured by this simulation. So here we can see that it is working, and this was actually related to other work, and it was matching. So the observation is that if we use a full-fledged solid element, then all sorts of stress components, that is the three-dimensionality of the elements, three-dimensional stress components can be captured at regions of interest. Most of the part of the laminate under this case is the stress state is 2D, but some portions at the edges are there where the stress state is 3D, and one of the three-dimensional component, mainly the transverse shear, is responsible for the edge-based filling, edge-based delamination. So there are other elements were also used, solid 73, solid 185. All of them are able to capture this phenomenon. This is a comparison. This comparison is shown. This is nothing but width to thickness ratio. So this was analyzed that if the width to thickness ratio, thickness is increasing, then the increase is very severe. Suddenly it rises. But if the width is small, then the transverse shear stress develops early, okay, and had a very high value. So if we want to avoid the transverse shear stress, but they will be at the edges or push them towards the edges, then the width should be taken higher. I mean, with respect to the thickness. So the width to thickness ratio should have a high value if we want to push the beginning of the transverse shear is towards the edge. That's the observation, and that's also confirmed and result from Nosier A and Bahrami A. So that was a 2006 work. So this with this I conclude my first part of presentation, where the case of a laminate subjected to a simple uniaxial stress, a laminate, not arbitrary laminate, but a symmetric laminate with a uniaxial load only, but that shows that it can also have complicacy. It can have three-dimensional state of stress at the edges, which can be captured by using a solid element. Now, why these shell elements are there? Shell elements are easy to use and they consume less computation time. So if you try to compare the elements in terms of computational cost, then of course shell elements are better, solid shell elements are better compared to the full-fledged solid elements. But the results are mostly reliable by solid elements. This is part 2 of presentation. This is a numerical simulation of impact phenomena on composite armor. So here motivation is that we have heard about armors, and the armors are mostly used for tank armors. They are very thick steel plates, homogenized armor plates. But body armors are also being considered nowadays, and composites being lighter weight, so composite based uh, armors are preferred for body armors. So from that perspective, this research was motivated. So the simulation model is prepared and some case study are run and discussion of numerical results considering normal impact conditions alone, and experimental results validation with there. But I will not have time to show the experimental results. Now, as I said that there is a growing need for the lightweight, high performance armors. Traditional metallic armors are used for tanks, and ceramic composite systems are being used nowadays. But we have to understand the ballistic behavior of ceramic composite well and see how the performance goes. A lot of literature review has been done. I am not going to read all of them, but just to say that this impact related research has been done for different types of projectile shapes, and it is actually done. The target is made of ceramic and composite armors, ceramic together with composite. Ceramic metal combinations have also been tried. So various types of armors can be tried. This is the literature review. So to study effects of projectile nose shapes, effects of multilayers, alternate stacking sequence of ceramic, then thickness distribution. How much will be the thickness of ceramic and composite for a given total thickness of the armor? That is one of the major issues. Now, selection of material models, since I talked about ceramic, 95% Al2O3, that is, as per the literature review, Johnson-Holmquist model is useful for modeling the ceramic. Hayhurst et al. Model proposed in 2001 is used for the FRP composite. The projectile that has been considered here is a deformable one. Many people does it with solid, rigid body, but it is not rigid body always. It is deformable, and it is made of 4340 steel. So that is why it is modeled by Johnson Cook. Okay. Now these are the mathematical relationships for Johnson-Holmquist JH2 model with the damage initiation criteria. So this time is not enough to explain all this. Then Hayhurst model for orthotropic material. Here the main thing is that whatever is the strain that is responsible for damage, so that is made of the volumetric strain as well as the deviatoric strain. So in order to include nonlinear shock effects, the total incremental strain is dissociated into volumetric and deviatoric strain elements. For this, the simulation result is better. And for the damage, initiation of damage, the Hashin's criteria is used. And if failure takes place in some direction, then its stiffness is set to be 0. Like here in this case, C11 is not there. So a failure in 1 direction has taken place. So this way modifications go, and it's a purely dynamic analysis. So this dynamic analysis, we will talk about the meshing of the plate or the armor, ceramic, Kevlar, composite armor. This is the Johnson-Cook strength model. This is very popular for material model of the metals. It is a steel. 4340 steel is used for projectile, which is deformable. Okay. So there are these damage constants D1, D2, D3, D4, and D5. They are evaluated actually in the simulation. That is an experimental part. So here the simulation has been done in Autodyne version. So total size is 150 millimeter by 150 millimeter. And this you can see that there is a ceramic front layer and there is a composite backing layer made of Kevlar 29 epoxy. And this is the projectile. Projectile is moving in the Z direction. The Z direction is the thickness direction. And when we discretize, the central impact zone of the target is discretized using finite element. That is to be done always because of the fact that there the strain gradients are very high. Impact is taking place there, and that is the zone where the finer mesh is required in order to capture the changes in strain, and not only strain, the strain rate changes. And the 4 faces at the edges of the target plate are clamped. By clamping means 0 rotation as well as 0 displacement, just like as if it is welded, right? Of course, this is debatable whether this is purely correct or not, but in this particular simulation work, it was done like that. Frictionless contact has been defined at the interface, and the front and backing plates are glued using the joint module. There is a joint module available in Autodyne. That means they have the same displacements so long they are not separated. These are the material properties for Kevlar 29, stiffness properties, strength properties, and 4340 steel. And these are given. These are some constants for this Al2O3. This is the ceramic density and other thing, and this is the JH2 model. Now this is the first result that you can see. One simulation result has been shown, and the plot is by residual velocity with initial velocity. Initial velocity is the velocity with which the projectile is fired. Here the projectile fired is with a plane velocity, I mean just a linear velocity in the Z direction, as I said, but there is no riffling action. Riffling means when some projectile is fired, suppose a bullet is fired from the rifle, then it also rotates. But here in this case, the rotation part was not given to the projectile in the simulation, only the translational velocity is given. And it comes in contact with the ceramic faces. Then if the velocity is enough, then it perforates and comes out with a velocity after perforating the composite. And that is called the residual velocity. So you can see that for a very high velocity, I think it was started with 1200 meter per second, 800, 600, 400, and with a velocity of around 423, approximately so, the red one. This is 300, sorry, not 423, this is 300, 335. 335. The residual velocity is 7.10 meter per second. That means just come out of the burner. So this is called the ballistic limit velocity. That means with this velocity, it just perforates. And if you look at this initial velocity 330 meter per second, then it is 0. 0 means the projectile does not come out of it, it gets short lodged. Short lodged, the shot is lodged. So here we define a term called ballistic limit velocity or BLV. BLV is nothing but there are two velocities actually. One velocity is the lowest velocity by which the projectile perforates, like here, 300 something. And another velocity is there, the maximum velocity for which the shot cannot perforate. The ballistic limit velocity is the average of the two. That is the way it is defined. That is why it is also called V50 velocity. Here the comparison with an work of 2016 is done. So the percentage error is noticed, and you can see one thing that when it was a very high velocity of 1000 meter per second, the percentage error is very less, minus 0.2%. This actually happens, the simulation is good or give correct result. We have also compared this with experimental results when the strike velocity is very high. But as it comes down, then gradually the amount of error, whether with some experimental result, increases. Of course, here the comparison is done with another simulation, and at a initial velocity of 330 meter per second, it is 3.5%. Still acceptable. Good comparison. And there is one more. Here it is a 12 millimeter thick bilayer target of alumina, that is ceramic is there, and 95% alumina, that is ceramic, and impacted by 340 steel, and this plate is 2024 aluminum. Here the striking velocity, the BLV is close to 400 something. The BLV has increased. This is because of inclusion of alumina. Of course, this is a metal, 2024 aluminum, and with ceramic. So this gives a relatively higher velocity, but the error is at 493 meter per second initial velocity, error is 8.67. Okay, so this happens. Now here there are other comparisons. Initial velocities are changing, 500, 600 to up to 1400, where the comparison with different researchers were done. And so our results also matched well with them. So that signifies the correctness of the simulation. So this is very important thing in simulation, just for the students, that whenever you are doing simulation, the simulation must be validated well. So long it is not validated adequately with other researchers' simulation or experimental results, your simulation should not be taken for granted as correct. Okay, that is very important part of any simulation. Why it is happening like this? It's reaching. Okay. So,
Sir, please go to the slide share again. Okay, now it's okay.
Jana? Yeah. So,
Yes, sir.
I don't know why it is happening. Anyway, uh, so here 10 millimeter dia and 41.7 gram blunt tungsten projectile that is impacted on a ceramic backed with a 12 composite. 12 means is Kevlar. So here also the residual versus initial velocity plot is there and compared with other researchers' work. And here we see that there is blunt nosed cylindrical projectile. The diameter is 7.56 millimeter, length is 30.54, and mass is 10.7. So when we actually tried to do comparisons for several impacts, because we are changing the velocity, strike velocity, but mass is kept constant for all of them, 10.7 gram, and mostly the diameter is 7.56. 7.56 millimeter is a standard diameter in defense application. So this way, length is adjusted in order to change the mass, because there are several types of nose heads we have used. One is the blunt nose, one is the ogive nose, and another is the conical nose. These three are uh, generally used, but most popular is the ogive nose. Okay, so target plates are meshed with hexahedron brick element. It is a 8-node brick element. One thing is very important in dynamic work, that we should not go for very higher order elements in case of dynamic simulation. We could have taken earlier in the stress analysis problem in the previous part, we had seen the solid element was taken as a 20-node brick element. But here we cannot afford to do that, because if we take 20-node brick element, then in the domain, in the actual domain, deformation domain, it can get heavily skewed. So there may be a problem in the simulation. Simulation may stop. So simpler elements like 8-node brick elements are preferred. That has been done. Thickness-wise element size is 1 millimeter, but in plane mesh size is reduced, particularly at the zone of interest. Now here you can see the simulation results at different times. This is the beginning, by 0 microsecond, 20, you can see the bulge, 40, the bulge has increased. Then here the shear plug is visible at 60 microsecond. At 100 microsecond, it is the projectile has come out together with a shear plug. This is for a, I think it's a low impact velocity. Yes, it is 500 meter per second. This is part A. So here you can see the damage is moderate. Okay. So there are two things in the domain. One part is the ceramic part, that is the first part where the projectile first confronts. Here it is a brittle material. So the concept of brittle material is that it absorbs a lot of impact energy and gets fractured. So brittle fracture. Then it comes to the Kevlar epoxy. The Kevlar epoxy, here actually there are different, it's a mixed filling. So we can also get to see the shear plug formation. The shear plug formation takes place by bulge at the back end. This is visible. In case of the 1000 or 1200 meter per second, at the same time, you can see the case. the bulge was there at 20 meter per second. At 40 meter per second, the projectile has come because it's a much faster impact. So whatever is expected, these are all visible. And these are the corresponding time versus velocity of the projectile. This has been captured. So you can see for 1200 meter per second, it has come and perforated, and velocity has become constant. For 1000, it has taken some more time before becoming constant. In 800, it has taken more time. 600, then this is 400, this is 200, it is still going on. And maybe, okay, it has possibly reached to 0. Then penetration time is also there. Penetration time is on the y-axis and initial velocity is the x-axis. Obviously, when the initial velocity is very high, penetration time is pretty low. So all these informations can be captured when you design your armor. So one thing must be kept in mind that when you are doing simulation, basically we are doing numerical experiments. When simulation was not there, then people used to do actual experiment. Actual experiment is always there, but actual experiment is time consuming and expensive. So in order to curb the expenditure and loss of material, loss of resources, one does simulation. But simulation must be correct and acceptable. Then only the simulation has some sense. Otherwise, it has no sense. It will mislead you. That must not happen. So therefore, adequate checks must be done in order to confirm the correctness of simulation. That is what is very important. So all these numerical experiments help us in taking decisions. Once the efficacy of the numerical simulation is established. There is some comparison. So it is, you can see that there are 3 cases, and in 3 cases, we have a bar diagram. The green one is 12 millimeter Al2O3 alone. That means the ceramic. If you do make a ceramic plate of 12 millimeter thickness and you impact it, the ballistic limit velocity will be around 150 meter per second. If you make it only with Kevlar, then the ballistic limit velocity is around 300, some 280, around 280 or 275 meter per second. That means any velocity more than 275 meter per second will penetrate or perforate the laminate or the armor. So in case here 150 is enough to perforate, here 275 or 280 is enough. If you put this 12 millimeter Kevlar with ceramic, then you get highest around 350 meter per second. Right? So this ballistic limit velocity tells you some information about the perforation. So the ballistic limit velocity is 22.73% higher when it is ceramic composite compared to only composite, and 110% more when compared to only ceramic. So although defense people are a little bit hesitant in using ceramic, but ceramic gives a better result in case of ballistic limit velocity. So here this for Al2O3 95, this thing, ceramic and Kevlar, the ballistic limit is 337.5. This is what is here. And what is the inference? What are the inferences? With the increase in incident impact velocity, residual velocity also increases. That is evident. A sudden increase in residual velocity can be seen just after the ballistic limit velocity. So this is another observation. These are some of the damage zone, damage mode in the target plates. So this actually, the damage zone or damage pattern for the ceramic part, front face of target. So this is the bulk failure, and you can see the most important evidence is that radial cracks. These radial cracks are typical for this bulk failure of the ceramic. Whereas this is predominated by delamination due to fiber breakage and other things, shear failure. And part of it is the plug formation, shear plug that comes out from the behind along with the projectile, if it perforates. And that is evident here. These are the shear failure zone. This one, and these are the delaminations. These are the main damage zones. Different types of damage zones here. So this is a ceramic, Kevlar, and epoxy target. We have put more attention to this. Projectile mass is 10.7 gram. So these are the damage zones. This can be generated from the AutoDyne. And these are actually showing the extent of the damage. What is also observed is that approximately 75% of the kinetic energy of the bullet is dissipated and is goes through the ceramic layer. The composite layer absorbs the remaining kinetic energy of the projectile and eventually stops it, if it can. But if the velocity is still high after passing through the ceramic layer, then of course it cannot sustain it. Now, we have also studied that what is the shape of the face, shape change in the projectile face. So this is for the change in length and corresponding strike velocity. Strike velocity means the velocity with which the projectile is initial velocity of the projectile. And here you can see if it is 1200 meters per second, then there is a lot of deformation in the projectile head. Okay, this I think the case of the blunt nose and the circular blunt nose has got an elliptic shape. And the 4340 steel projectile eroded more at higher impact velocity. That is expected. Negative and positive sign indicates decrease and increase. The effect of the projectile mass. Here the projectile mass have also been tested. What happens if we change the projectile mass? So for that we kept the diameter same, but the length is changed, and accordingly the mass is changed. As the mass is changed, ballistic limit velocity is decreased. When it was a low mass, then 485 meters per second is the velocity. But when it is a 15.6 gram, slightly more than double, 2.5 times almost, 255 meters per second is the ballistic limit velocity. So this is the plot. And these are the corresponding graphs for the residual versus initial velocity. And here the mass is kept constant, and in order to keep the mass constant, there is change in the diameter and length of impactor. the ballistic limit, there is not much appreciable change. That means the mass plays a crucial role, not the diameter and the length. It is the mass, because mass is carrying the kinetic energy, half mv square, and which causes the damage. Some comparison is also done for different nose shapes, as I said. The blunt nose has been talked about. This is the ogive shaped nose. Diameter is 7.56, and this head part of the ogive shaped nose is also 7.56. And the length is kept 26.2 millimeter, and accordingly calculations are done in order to keep the mass same. Mass remains fixed as 10.7 gram. Similarly for the conical head also, here this conical head length is 9.1 millimeter. Accordingly, the length of the other part is changed to keep the mass same. So here the simulation result. Yes.
Sir, sorry to interrupt you. If you just allow the audience to ask some questions, kindly can you wrap it up within 5 minutes so that audience can have 5 minutes more for question answering?
Yeah, I will just take 5 minutes more.
Okay, sir. Thank you so much.
Yeah, I have kept a clock in front of me.
Okay, sir. Okay, sir.
It
Fine.
shows that 10
Fine.
minutes to 8. I will stop at 5 minutes to 8.
Okay, sir.
Yeah.
That's great.
So these are the plots for blunt nose, ogive nose, and here you can see that the velocity, strike velocity, and the time. This is velocity versus time of perforation, etc. Residual velocity. So blunt nose gives a velocity of 312.5 meter per second. Ogive nose 207.5 ballistic limit velocity. Conical is 265 meter per second. It means that if we are using a blunt nose, perforation will take place after a velocity of 312.5 meter per second. Whereas for the ogive nose shape, it will perforate at 207.5 meter per second. So earlier we were discussing from the armor point of view, how we can make a armor strong. But if we want to make a study from nose shape point of view, projectile or the bullet point of view, then ogive nose performs the best because it can perforate the plate at the lowest speed, just because of its nose shape. That is why in all defense applications, ogive nose are used, and that is validated in our simulation. Okay, so there are other variations, many kinetic energy projection versus time, energy dissipation versus time, then energy absorbed by composite layer versus time. So when you do simulation, it is an added advantage that you get to see many things at the same time. So this is another thing, that comparison of the three nose heads. Deformation of the three nose heads. Maximum deformation takes place in case of blunt nose. Conical and ogive nose undergo a little bit of lesser thing. So ogive performs better. Layering and stacking sequence is another aspect. I just tell you the crux of this simulation, that we tried to see that suppose we have going for a 10 millimeter plate or 10 millimeter armor. So out of which, how much thickness we will give to ceramic and how much thickness we give to composite? Is it 50%, 50%, 5 millimeter, 5 millimeter, or more for composite, less for ceramic, or more for ceramic, less for composite? So here something was done, and it was found that best combination was found for A6.4 K3.6, means the 6.4 millimeter thickness of ceramic. It is written A because alumina, I mean 95% alumina. 6.4 millimeter ceramic thickness, 3.6 millimeter Kevlar thickness. And at an initial velocity of 220, it gets stopped. Whereas here it goes on for the residual velocity. Even at 170, this is for this layer kind of thing. So best is 6.4, 3.6. Here we can see that ballistic limit velocity in the bar chart. Highest is obtained by this combination 6.4, 3.6. So summary, I think I have told you already during the presentation. So if you have any question, you can ask me at this stage. You have 5 minutes. Any
Yes,
question?
sir. I think in the chat box, Mr. Projanno De, he has asked which one is better for ultrasonic wave propagation simulation, ANSYS or COMSOL multiphysics?
Okay, I have not done any work on COMSOL, but what I can tell you is that if you want to simulate ultrasonic wave propagation, it is also a dynamic problem. You give an initial pulse and then withdraw the force and the disturbance proceeds. So it advances. Nowadays, softwares are equipped that they choose the time step automatically. But when you discretize, you have to be careful that the mesh size should be small enough and should not be large. At least wavelength of the wave, and at least in one wavelength, eight nodes should be there. This is a Ceron's criteria. And time step you don't have to check because software automatically detects the time step. Every time it has to calculate displacement, velocity calculation. And the choice of element should be simple, as I said earlier. So better go for 4-node element. If it is an isotropic domain, you can take a 4-node quadrilateral element, but do not go for 8-node element. That is my advice. Yeah. Anything else?
Sir, I think one more question has arrived from Mr. John Alexis. Sir, is there any model analysis done during this analysis?
Which one? I please repeat.
Sir, is there any model analysis done during this analysis?
Modal analysis. I think modal. No. Modal analysis is done.
Okay, modal. Okay. Okay.
Perhaps you wanted to say modal.
Or maybe, sir. I think the audience, you can raise your hand and so that we can unmute you and you can directly talk to sir. Anyway, sir.
Is it done?
Yes, modal, I guess. And another question from Mr. Pojanno De, he asked once again, I want to increase the non-linearity of material manually. Is it possible in ANSYS?
Yeah, it was done actually in Autodyne. Autodyne is a part of ANSYS, and yeah, you want to say that the material is nonlinear. If you want to incorporate that nonlinearity, yeah, it should be done. Maybe you have to write some sub-program for that. Nowadays, it is possible in ANSYS. Like in Abacus, we write UMAC. Such things should be possible in the material model. Uh, yeah, it may be done. Hmm.
Sir, I think there is another question. Is it comfortable and convenient to use peel ash for composite material? Mr. Satya Prasad.
Comfortable and convenient to use.
Convenient to use peel ash.
Steel ash.
Peel ash. P-E-E-L, peel ash for composite material.
No, not for impact applications. Impact applications, it should be fiber based. In fact, even one unidirectional fibers are also not recommended. It must be cloth based. The composite must be made of cloth, like Kevlar 29 cloth has been used in this case. They should be used for impact applications. If for other applications where the loading is not high, in that cases, ash may be used as one of the elements of composite, but not for an impact application. I don't think so.
Okay, thank you so much, sir.
Hello, sir.
Because
Hello, ma'am.
actually so many questions.
Hello,
Okay,
ma'am.
okay, please
Uh,
continue. Dr.
hello,
Naveen
Professor.
Kumar.
This is a wonderful session, sir. Actually, from starting to advanced research. So, thanks for the wonderful session, sir.
Thank you, thank you.
Yes, sir. Actually, in the simulation part, composite simulation part, how we can control the element numbers, sir. Actually, so I'm unable to control the element numbers. So due to that, I'm getting variation in each and every trial. So I cannot able to fix the values actually. So how I can control it, sir? Is there
No,
any tip from your side,
actually,
please?
you don't want to control or define the element numbers. Rather, depending on the domain size, you have to choose the element size.
Okay.
Once you choose the element size, then element numbers, node numbers are automatically defined.
Okay.
There
But
is a
some.
preprocessor built in the software. That
Okay.
preprocessor takes care of that.
Okay. Okay. Okay, sure, sir. I will follow your articles for better understanding of those concepts. Thank you so much, sir.
Thank
So,
you.
thanks for inspiring us. Thank you.
Thank you.
Thank you so much, sir, for this wonderful session actually, and it is quite informative. And thank you once again for sparing your valuable time to be with us today. And audience has so many questions waiting in the chat box, I know, but you should understand that we have some time constraints definitely. So we'll be sharing your questions to sir, and we'll be sharing sir's emails and other details so that you can talk to sir later. You can have your answers directly from sir. So thank you so much, sir, for this session
Yeah,
once
thank you.
again.
But before signing out, I would like to mention Dr. Krishna Vishwas, who has done PhD under my guidance. He actually carried out these simulations, and we jointly worked together. And so I express my sincere thanks to him for his time, devotion, and labor in carrying out the simulations and doing the work. So thank you all for giving me this opportunity. Thank you once again. So with this, I am I have to sign out, I think. I am closing
Yes,
the
sir. Thank you so much.
presentation. Okay.
Okay, sir. Okay, sir.
Okay.